Hey, welcome back and welcome to Casual Friday. In this chapter, we're going to talk a whole lot more about the periodic table. We've mentioned it in the past a little bit, but we're going to go into a little bit more detail starting now. Let's do it. The history of the periodic table actually begins with a guy named Antoine Lavoisier, who lived in the 1700s, and Antoine put together all of the known elements at the time. He arranged them into 4 categories. There were 33 elements in his table of elements, and it included such things as silver and gold, carbon, oxygen. But as we continued into the 1800s, more and more technology became available. The development of electricity was helpful in breaking down compounds into elements. And then later on, the spectrometer was developed, and that helped us as well. By around 1870, we went from 33 elements to around 70 elements in total. And as we discovered new elements, that meant more and more research regarding those elements and the compounds that they make. So naturally, there had to be a good system of organization in compiling all these things. One step that was really important was in 1860, when chemists decided on a uniform way of determining atomic mass. That allowed chemists to be able to share their work more easily and for one chemist to understand what another one was doing. In 1864, a chemist came along whose name was John Newlands, and he proposed a new way of organizing these elements. It involved something that he called the law of octaves. You see, Newlands noticed that with about every 8th element, the characteristics of those elements tended to repeat themselves. Newlands suggested then that just like there were 8 tones in a musical octave, so we would have this law of octaves for chemistry. Well, the thing was, it didn't really catch on because it didn't work for all the known elements. That was one problem. And for some reason, scientists at the time had kind of a dim view of equating music to chemistry. So since the law didn't work for all the known elements, and scientists didn't like the musical analogy, the law of octaves, it seemed, kind of fell on deaf ears. No? Okay. So then in 1869, along come 2 scientists whose names were Lothar Meyer and Dmitri Mendeleev. Now you may have heard that latter name because he published his findings first. Kind of got on the board that way. Each of them were able to demonstrate that there was a connection between atomic masses and these properties of the elements. So Mendeleev noticed that when he arranged the elements in increasing atomic mass, there was this periodic pattern in their properties. Periodic pattern properties. So he arranged his table according to increasing atomic mass, and he used columns, putting like behavior elements together. Mendeleev's table was used more because he was even able to predict elements that were yet undiscovered. Ones like scandium, gallium, and germanium. He simply left a spot in his table for those. He had all the information about them. They just hadn't been discovered yet. Pretty amazing. The thing about it was, Mendeleev's table wasn't entirely correct. As more and more elements were discovered and their masses more correctly determined, it was found that some things were frankly out of order. And it was found that some elements were in the same column with others that didn't have the same chemical properties. But in 1913, English chemist Henry Moseley figured out why that was. You might remember that Moseley was the one to discover that atoms of a certain element have a unique number of protons in their nucleus. When Moseley rearranged the elements in the periodic table according to increasing atomic number, the problems were solved. And you could see a clear periodic repetition of chemical properties in the table. That concept, where there are periodic repetitions of chemical and physical properties of the elements when they are arranged by increasing atomic mass, is called periodic law. You might recall we said that the vertical columns in the periodic table are known as groups. The horizontal rows in the periodic table are called periods. So beginning with hydrogen, we have a total of 7 periods. The columns or groups are numbered, as you can see, from 1 to 18. Now take a look for a moment at the tallest columns. Group 1, 2, 13 through 18. These are the groups that we call representative elements. Groups 1, 2, 13 through 18. Sometimes they're even called main group elements. The elements in groups 3 through 12 are known as transition elements. So we have metals to the left side and nonmetals to the right side, and in between the two, something that we call metalloids. No, they're not scary. They're not monsters. You'll see. They're pretty normal. Let's talk about metals first for a moment. Metals are shiny when they're smooth and clean, for the most part solids at room temperature, and they're really good conductors of heat and electricity. In addition, metals are very malleable and ductile. Those are fancy words that means you can shape them into plates or sheets, and ductile means you can draw them into thin wires. Now, much of the representative elements and all of the transition elements are metals. You can see that the large majority of things on our periodic table are in that classification of being metal. By the way, starting around boron, do you see that zigzag line that's going down? That is the boundary between metal and nonmetal. Now, some of our groups have special names that you need to know. Group 1, with the exception of hydrogen. Hydrogen isn't really a metal, okay? But the metals that are in group 1, those are known as alkali metals. Those metals are extremely reactive, so much so that we don't really find them by themselves in nature. We find them compounded with something else, like say oxygen. So we'd have sodium oxide instead of just sodium. Next to the alkali metals, we have the metals of group 2, and those are known as alkaline earth metals. Now those are pretty reactive too, ones like calcium and magnesium. Again, we don't generally find them by themselves because they're so reactive. Now from groups 3 to 12, we have what are known as the transition metals and the inner transition metals. The inner transition metals are those two rows on the very bottom, in between group 3 and group 4. And frankly, many times you'll see those separated from the rest of the periodic table and placed on the bottom. The top row of inner transition metals are known as the lanthanides because they come right after the element lanthanum. The bottom row of inner transition metals are known as the actinides because they come right after actinium. But all the rest of those metals in groups 3 through 12 are the transition metals. Now let's talk about the nonmetals. Those are on the extreme right side of the periodic table. And nonmetals are typically gases, or if they are solid, they're dull and brittle. Unlike metals, nonmetals are not good conductors of heat or electricity. There's only one nonmetal that's a liquid at room temperature, and that's bromine, element number 35. Incidentally, I forgot to mention that there is one metal that's a liquid at room temperature, and that's mercury, number 80. There are a couple of groups in the nonmetal section that have special names, and we need to be aware of those. Group 17 is a set of very reactive nonmetals known as the halogens, ones like fluorine and chlorine and bromine and iodine. Again, they're very reactive, so we usually find them in a compound and not by themselves. Group 18 is a group that we've previously mentioned. Those are known as the noble gases. Sometimes they're known as inert gases because they are very unreactive. The last classification we need to mention are those elements along that stair-step line. Those elements have a combination of characteristics of metals and nonmetals. We actually call them metalloids. No, they're not monsters. They're fine. They're actually very useful. When you get go. Anyway, metalloids like silicon and germanium are used in computer chips. Elements like silicon are even used to make prosthetics. So no, metalloids aren't monsters. They're quite useful. That's the end of our introduction to the periodic table. We'll of course talk much more about it in the upcoming sections. We talked a little bit about the history first of the periodic table, and then we talked about some of the different categories within the periodic table. I hope it's been informative for you and helpful. Until next time, God bless.